So far, we have a way of finding an approximation to the area under a curve using rectangles. But how do we find the exact area? Well, here I have a curve drawn, and let's say I'm interested in finding the exact area under the curve between 0 and 6. Well, using two rectangles, we can see I have an over-approximation. I'm overestimating by all this amount right here. If I use four rectangles to approximate the area, I still have an over-approximation, but now it's a little bit closer to the exact area under the curve. There's less overage happening. And if I use six rectangles, that's even less of an overestimate. So I'm getting closer and closer to finding that exact area under the curve if I use more and more rectangles. And that's not a coincidence. The more rectangles I use, the better approximation I'm going to get. But it turns out we want to consider increasing the number of rectangles infinitely. So we're going to bring in the concept of limits, and we're going to think about what happens as the number of rectangles goes to infinity. Here we have a theorem. It says if f of x is continuous on the interval from a to b, then the endpoint and midpoint approximations approach the same limit, L, as n goes to infinity, where n is the number of rectangles. So in other words, if we consider a limit as the number of rectangles goes to infinity of the right endpoint approximation, that's the same as the left endpoint approximation, and it's the same as the midpoint approximation. So it's ultimately not going to matter which we use to define the heights, the right, left, or midpoint approximation, because as we make the number of rectangles go to infinity, they will all equal the same value, and we're going to call that value L. And it turns out L is the area under the curve from A to B, the exact area under the curve from A to B. So the rectangular sums we have been finding are more generally called Riemann sums. So we're going to take a closer look at that. Let's informally talk about Riemann sums. A Riemann sum is a rectangular approximation for the area bounded between a curve and the x-axis, with the property that the width and the height of each rectangle can vary. So if we look at this picture over here, we're interested in the exact area from A to B under this curve and above the x-axis. And we have been looking at the case of using rectangles of equal width and then picking specifically the right endpoint for the height, or the left endpoint for the height, or the midpoint for the height. But what we could do to get an approximation is use rectangles but change the width and the height of each and every one so that we get a pretty good approximation using rectangles. We can choose the right endpoint for one and then maybe the midpoint for another one. So those are in general called Riemann sums. So our rectangular sums using right, left, and midpoint are like special cases of Riemann sums. So here, a Riemann sum, we're still going to use sigma notation, is the sum from I equals 1 to n of f of x of I star delta x. So what's going on here? It just means that x of I star is any x value in the ith interval, so we can choose any x value in the interval to define the height. So right, left, and midpoint approximations, they're all just special cases where we pick a specific one as opposed to just picking any x value and using its corresponding y value as the height. Now we needed the idea of Riemann sums to talk about the formal definition of a definite integral. So what we have here is if a function is defined on this interval from a to b, with the interval from a to b broken up at these values, x1, x2, xn, and all the Riemann sums, not just the endpoint and the midpoint approximations, but any possible Riemann sum, so collection of rectangles used to approximate the area, if all of those Riemann sums approach the same limit, L, as the width of the largest rectangle approaches 0, I'm going to pause right there for a second. If there's infinitely many rectangles, the width is going to have to get really, really tiny. So the width of the rectangle will have to go to 0. Then the definite integral from a to b is given by, so the integral from a to b of f of x dx, it's actually a limit. It's the limit as the largest width of the rectangles goes to 0 of the sum of the Riemann sum. So basically all we're saying here in a more formal way is that to find the exact area under the curve, which is a definite integral, we want the limit of any possible Riemann sum to have all the widths go to 0, get really, really, really thin and tiny. We're going to add up all those rectangles, and that exact value, L, is the exact area under the curve. And if this limit exists, then we say f is integrable on the closed interval from a to b. So this is a super formal way of defining a definite integral, similar to when we defined a derivative as the limit of a difference quotient. So here we're saying a definite integral is the limit of a Riemann sum. Let's briefly talk about notation. This is read as the integral of f from a to b, or the integral from a to b of f, and then this is the integral sign. These values here are the limits of integration. The function f of x in this case is the integrand, and dx is called the differential. In this example, we want to evaluate the following integral using the limit of Riemann sums with right endpoints. So here we're interested in what's the exact area under the curve x cubed plus 6x evaluated from 0 to 3. That's what we want to find. And to do that, we're going to do the limit of a Riemann sum specifically with right endpoints. Now, in the definition we just saw, it technically doesn't matter what Riemann sum we use, because the limit of all the Riemann sums, because the rectangles are getting really, really, really small or thin, it's going to give us the exact area. So it doesn't really matter if we use right endpoints, left endpoints, midpoints, varying heights. So we can choose any we want. The reason why we're choosing right endpoints is because we have a nice formula for it that we developed already earlier. And it's going to allow us in a bit to use some known precalculus formulas. So we're going to use our right endpoint formula to evaluate a definite integral. Now, I'm going to go ahead and do some scratch work off to the side before I actually, move forward with this integral. So I'm going to pull the function over here. I'm going to remind ourselves that f of x is x cubed plus 6x. And I'm also going to remind ourselves that a and b are the limits of integration, so a is equal to 0 and b is equal to 3, so that I can start to find this f of a plus I delta x times delta x quantity. All right, so a is 0, so that's nice. How do we go about finding delta x? Well, delta x had a formula. It was b minus a over n. So we have 3 minus 0 over n, which is just 3 over n. So there's my delta x. And so this problem, in order to do the limit of this sum, I need f of a plus I delta x. So I need f of 0, which is a, plus I times delta x, which is 3 over n. So I need f of 3i over n. That's the quantity I'm going to need to do this limit of this Riemann sum. So I have to plug 3i over n into each x in the f of x function. So f of 3i over n is going to be 3i over n cubed minus 6 times 3i over n. And I'm going to multiply a little bit of what's going on in here. So 3 cubed is 27i over n cubed minus 18i over n. So f of 3i over n is this difference here, and that is f of a plus I delta x. And then delta x is just 3 over n. So I have all of this scratch work ready for me to move forward with doing this definite integral using this formula. So let's do it. So this is going to be the limit as n approaches infinity. So I'm just directly using this formula here. As n approaches infinity of the sum of I equals 1 to n of f of a plus I delta x. Well, we just did all that work. That was f of 0 plus I times 3 over n. And working that all out, we got this. 27 I cubed. Just caught that. Good thing I did. Sorry about that. 3 was cubed and I was cubed. And then over n cubed. So we have 27i cubed over n cubed minus 18i over n. So all of that is f of a plus I delta x, and that needs to get multiplied by another copy of delta x, which was 3 over n. So there's a 3 over n that's also being multiplied. All right, so what I'm going to relate it to is just like we did the formal definition of a derivative as the limit of a difference quotient. We often did the scratch work on the side of the difference quotient algebra before doing the limit of the difference quotient. So that's basically what we did here. Definite integral, the limit of a Riemann sum. I did the scratch work on the f of a plus I delta x part before I substituted it in. Now, I'm going to distribute in the 3 over n. So I have the limit as n approaches infinity of the sum of I equals 1 to n of, let's see, 81. Oh, whoops. Man, making little mistakes all over the place. This should be a plus. All right, I don't know how I turned it into a minus. No, maybe because I turned it into a minus over here. So this is plus and this is plus. See, we always need to go back and just double check. This is small things that we miss, right? The negatives. All right, so here, this is going to be 81i cubed. Go back to blue here. 81i cubed over n to the 4th. So we're multiplying the n and n cubed. And then plus 54i over n squared. So again, just distributing 3 over n to each term. And then what I can do is I can break this up into 2 summations. So this is the limit as n approaches infinity of the sum of I equals 1 to n of 81 I cubed over n to the 4th plus the sum of I equals 1 to n of 54i over n squared. All right, so I turned it into 2 summations. And now I can take out of a summation any constant. So the constant that I can pull out is 81 over n to the 4th. So yes, n is a constant. The only thing that's treated as a variable in a summation is the indexing variable on the bottom. So in that case, I. So this is going to be the limit as n approaches infinity of 81 over n to the 4th, the sum of I equals 1 to n of I cubed, plus, same thing here, I can take out 54 over n squared to be left with the sum of I equals 1 to n of just I. Whew, okay. So now, these sigmas, these summations, have nice formulas that we need to recall from precalculus. So I've just made some space here, and I've included the precalculus formulas here on the bottom. So the sum of I equals 1 to n of I cubed is on the bottom right here. It's equivalent to n squared times n plus 1 squared over 4. So I'm going to replace this with n squared times quantity n plus 1 squared over 4. But I'm going to leave the 81 over n to the 4th. And we still haven't evaluated the limit, so that's got to stay. And then plus 54 over n squared stays. And the sum of I equals 1 to n of I has a nice formula. It's n times quantity n plus 1 over 2. So with these formulas, we were able to drop the sigma notation. And now we can just evaluate this limit at infinity, or really these two limits at infinity, because all we have left is rational functions. So the rational functions that we have left, if we compare, we're talking about end behavior, limits at infinity, we think end behavior or asymptotes. So we have n squared on the top, so n to the 4th. And then on the bottom, we have an n to the 4th. And if the degrees match, then we're allowed to just take the leading coefficients, which would be 81 over 4. So the answer to this first limit at infinity is just the coefficients 81 over 4. And the same thing's going to happen over here. I have n squared, so the same degree. So I just take the coefficients, which are 54 over 2. So we have plus 54 over 2. And the limit is gone because we just evaluated it. And so we're just going to add these two numbers together. So common denominators, this is 108 over 4, which is 189 over 4. That's the exact area under the curve, x cubed plus 6x, from 0 to 3.